Welcome to lecture 15. In the previous lecture, we had derived simplified forms of the momentum equations. The most simplification happened with the z momentum equation because of the fact that the vertical extent of the motions is much less than the horizontal extent. And going back again to the previous slide to show you what we had discussed. So we had shown how the x momentum had simplified. This f star term had gone away. The y momentum equation and the z momentum equation, which had the most simplification, and continuity equation remains the same. We have done all of these in the previous two lectures. So these are A, B, C, and D, and there's a reason why we have labeled these equations. Now, as we discussed in the previous lecture, we'll look at the energy equation. So in lecture 9, so we had written down, where we had discussed Boussinesq approximation. So we had written down the energy equation in terms of temperature for an incompressible fluid. So let's get to the energy equation in terms of temperature for an incompressible fluid. The total derivative of the temperature is equal to kappa the Laplacian of temperature, where kappa, this kappa T is the kinematic diffusivity of heat, in the fluid, and this is equal to kT over rho naught Cv, where kT is the thermal conductivity. The thermal conductivity over rho naught Cv. This is what we had derived, and you can go back again to the previous lectures. And the reason why this is of a simpler form is because of this incompressibility that we had invoked. So we got rid of the divergence of the velocity terms, and this is what we are left with. The total derivative of temperature is proportional to the Laplacian of the temperature, and the proportionality constant is the kinematic diffusivity of heat. So this is within the Boussinesq approximation. Kinematic diffusivity is written as kT over the thermal diffusivity by rho naught Cv. Again, as you can see, there is this rho naught, so we have Boussinesq approximation. So now this equation, this dt, this total derivative of temperature is proportional to the Laplacian of temperature, is isomorphic to the salt equation. So if you look at the salinity evolution equation, this is both of these look similar. So the total derivative of the salinity, some kind of a measure of concentration of salt in water, is equal to the kappa is Laplacian of salinity. So now, using the equation of seawater for equation of state for seawater, so remember that just for pure water, a single component, just pure water without any temperature, without any heat content, or without any salinity, the equation of state is just the density equal to constant. However, for seawater, the density varies with the heat content in the water and the salt content in the water. It also changes with pressure, but we have tried to not take into account the variation of density with pressure because the variations are quite small. And again, this is again a recap. We have already done this. We have written down the equation of state is 1 rho naught into 1 minus alpha delta T plus beta delta S, where delta T and delta S are the changes in the temperature and salinity respectively, and alpha and beta are the thermal and haline coefficients, coefficients for contraction and expansion. So now defining this perturbation density, defining rho prime equal to rho minus rho naught. Okay, so remember that the total density, this here rho is the total density. This is where we might be confused here. So rho is total density only in the equation of state. In all other equations that we have derived, rho is the fluctuation density. Only in the equation of state for seawater here, the rho is the total density. Okay, hence we have defined a rho prime as the fluctuation density. We'll see why we need this. So now just taking the total derivative of this rho prime and just plugging in the definition, the equation of seawater, we have minus rho naught alpha kappa t del square t plus rho naught beta kappa s del square s. So it is important for you to verify that this is correct. So this is just a one-step process. I'm just taking the total derivative of the fluctuation density, and I'm using using these two equations, the energy equation and the salt evolution equation. So now we have this form of the total derivative of the fluctuation. Now this is something which we have not yet introduced, but which is called turbulent flows. And turbulence is something which we'll get to the end of this course, is something which mixes both salt and heat in equal manner. So here in the previous slide we had a different diffusivity for heat and a different diffusivity for salt, kappa s and kappa t. However, if the flow is turbulent, and this is generally the case for large scale geophysical flows because the Reynolds numbers are very high, so those flows are mostly turbulent. And if the flow is turbulent, it mixes both salt and temperature in the same way, and hence the diffusivities can be assumed to be same. So this is not certainly true for molecular diffusion, because we know that the salt diffuses very differently from temperature, and whereas in a turbulent flow they both diffuse with this similarly. That means they lose their concentration in this within the same time frame in a turbulent flow. So this is an approximation, and hence you have to be careful when to apply this approximation. We have to know that this applies only to turbulent flows. So in a turbulent flow, the kappa t is approximately equal to kappa s. So anything that you put into a turbulent flow, it will mix it because it's turbulent, and it will mix it at the same rate. And this is certainly away from molecular dominated diffusion regime. So hence the energy equation can be written as so the energy equation can be written as something like the following. So we are dropping the prime okay. So this is the final form of the energy equation, and let's write it let's call it, number it, label it as equation E. So now the above set of equations, and I told you that we are labeling them because of a reason. So the set of equations from A to E are the fundamental equations that are used in numerical geophysical flows. And these are called the primitive equations. So it's this is the reason why we had done all these simplifications and why we had done the scale analysis to get to the simplified form. I'll show you again the equations A, B, C and D that we discussed in lecture 14. So A, B, C, D, and this is the E, this is the energy equation. So all of these combined are called the primitive equations, and these are the bedrock of geophysical fluid dynamics. So and in the equations that are there in A and B, this I'm going back to this slide from lecture 14. So this is the molecular viscosity. This is in numerical simulations, computational simulations of geophysical flows, this molecular viscosity is replaced by turbulent viscosity. So turbulent or the eddy viscosity. So we'll learn about what is this eddy viscosity later in our course. So this is replaced by eddy viscosity, and it is also the reason why we could do this, why we could make this assumption. Kt equal kappa t is approximately equal to kappa s, which allowed us to simplify this density perturbation equation, the total derivative of density, and we could write it in this simplified form, the energy equation. So we'll discuss the eddy viscosity later, but this is just to mention that in the full primitive equation, these will be replaced by the eddy viscosity. And hence we finish the discussion on the primitive equation, which is very central to geophysical fluid dynamics. So equations from A to E, A, B, C, D, E, all the 5 equations are called together called the primitive equations. Now it's important for us to understand certain dimensionless numbers which can be created from the various parameters, various forces, various terms in the momentum equations. And this is just, whatever I'm going to discuss next are just some representative dimensionless numbers. There you could create dimensionless numbers based on the physical processes that you are interested in, and it could be in a different manner also. But I am discussing the most common dimensionless numbers that we can derive and which are of importance in geophysical flows. So dimensionless numbers are, so they are ratios of different physical quantities. So anyone who has had a course on intermediate fluid mechanics will know that, will know what dimensionless numbers are. In case you need a recap, they are just ratios of different physical quantities, as I already mentioned. So their magnitude helps us their magnitude helps us In understanding the relative importance of different terms in the governing equation. Okay, we'll see how that is helpful for us. So now we'll start with the primitive equation. So we'll write down the primitive equations again. So the x momentum equation, del u del t plus u dot del u minus fv equal to minus 1 by rho naught del p del x plus nu del square u. The y momentum equation being del v del t plus u dot del u, so del v plus fu minus 1 by rho naught del p del x plus nu del square v, new Laplacian of v. So now expanding this whole equations in, because we have the concise form, so just for our to be more clearer in the scale analysis, so the x momentum equation similarly we can expand the y momentum equation. So the terms and you can just do it expand similarly. So the terms scale as u by t, u squared by l, u squared by l, wu by l, sorry, this wu by h because there is z here, omega u because scale for both v and u is capital U, p by rho naught l, nu u by l squared, nu u by l squared, and nu u by h squared. So in the non-rotating case, so we're discussing non-dimensional numbers. So in the non-rotating case, many of you may have been already exposed to this non-dimensional number. The most common non-dimensional number is called the Reynolds number. Number Re, I mean, is a symbol which is commonly used for Reynolds number. Sometimes books also use the symbol R, just the alphabet R, capital R. So, but we'll try to use Re. Inertial forces by viscous forces. Now looking at which are the terms which gives us the idea of inertial forces. So this is the inertial term, and the viscous terms are these terms. Okay, so hence the ratio of the inertial forces and viscous forces is, if you write it term wise, is u squared by L, nu u by L squared equal to UL by nu. Okay, so from the previous scale analysis, we have derived a non-dimensional number, which is a ratio of the different physical forces. And this is what we had also mentioned previously, that non-dimensional numbers are ratios of they're ratios of different physical quantities. Okay, so here we have created a ratio of forces, the inertial forces to viscous forces, and we have the Reynolds number, which is a very commonly used non-dimensional number. So this is this might be something of interest to you. So this is named after Osborne Reynolds. So Reynolds is the last name of the person. So he was a British engineer, and the Reynolds number is named after him. And he has a very interesting experiment, and you can go and look at the experiments of Osborne Reynolds and how he inferred some early transition from laminar to turbulence situation. So now, by definition, geophysical fluid dynamics are affected by rotation. I mean, geophysical flows are affected by rotation, and this is the premise that we have always been emphasizing, that rotation and stratification are important concepts in geophysical flows. So hence we need to create a non-dimensional number that takes into account the effect of the rotation. So a natural extension of this one, so we had created a ratio out of inertial forces and viscous forces. Let's try to create a ratio of inertial forces to the Coriolis term. So the ratio of inertial forces to the Coriolis gives us, so the inertial forces are u squared by L, the rotation terms are omega u, so this is equal to, this is equal to u by omega L, and this is again very commonly used in geophysical fluid dynamics, but may not have been introduced yet in some fluid mechanics courses, because the rotation term is generally not important in some other situations that are of focus in intermediate fluid mechanics courses. But this is a term, this is of importance to us. This is the ratio of the inertial forces to the Coriolis forces, again because of the fact that rotation is so important for geophysical flows, and this has been named as the Rossby number, and this is denoted by the symbol RO. Okay, so this is we are denoting it by symbol RO, and this is named after again a scientist, which might also be another thing that is of interest to you. So this is named after Carl Gustav A. Rossby. So he was a Swedish meteorologist, and he had a lot of contribution to understanding weather phenomena, and this number has been named after him. So this is comparing, I mean, look at the similarity of the Reynolds number to the Rossby number. It will be easier for us to recall later on. So Reynolds number is inertial by viscous forces, Rossby is inertial by rotation. Yeah. So this is inertial terms by the Coriolis terms. Earlier it was inertial terms by the viscous terms. Here it is inertial term by the Coriolis terms. So it's easy. I mean, that means, this will help us in remembering it, recalling it later on. So it's important because the characteristics of geophysical flows now vary with difference in the Rossby number. Okay, so if the rotation strength is different for a certain flow, the characteristics of that flow will be different from somewhere where rotation strength is less, keeping the inertial terms same. I mean, the magnitude of inertial terms same. So this is of importance when rotation comes into picture. Of course, if there is no rotation, you cannot define a Rossby number. So as previously discussed, P by rho naught QL is of order unity. Rho naught U omega L is of order unity. I mean, we are looking at all the terms of the momentum equation that we had done a scale analysis. I mean, we are looking at now the ratio of this one and the rotation term, and we know that the pressure over the rho naught L omega U is of order unity because pressure scales as rho naught L omega U, and we've discussed this previously. So this is of order unity. So the scale analysis, I mean, the ratio gives us just a number which is near about 1. So now the ratio of the frictional term to Coriolis So now the frictional terms, that is the viscous terms, so viscous terms are also called frictional terms because viscosity is representative to the friction between two different layers. Okay, so so ratio of the viscous, actually it's better to write it in parentheses. So ratio of frictional or the viscous terms to Coriolis they give us nu U by h squared omega U. So now again, as with the other two quantities, this ratio is also given a number. So this is called, this ratio also has a name, sorry. So this is called the Ekman number. This is represented by the symbol Ek, and this is nu by omega h squared. Okay, so this is the ratio of the viscous or the frictional terms to the Coriolis. Okay. So again, the Ekman number is named after a person, a scientist. This is a Swedish oceanographer. This is V.W. Ekman. So these are just some things that I feel might be of interest to you, where the history of where this the naming of these numbers of these non-dimensional quantities come from. So he was a Swedish oceanographer and had significant contribution to understanding oceanic flows, and most importantly understanding flows near the boundaries. And we will see later on that how this effect of this the friction or the viscous terms appear near the boundaries, and this I've also previously said that in most large scale flows away from the boundaries, we say that the frictional effects are negligible, whereas near boundaries this is not so, and this gives rise to interesting dynamics. We'll see how this Ekman number will keep appearing, and how this person's name, the scientist's name of Ekman, will again appear later on when we do studies of the importance of the viscous forces in geophysical flows. So this is actually a small number. If we only take into account the molecular viscosity, this is a small number for geophysical flows. So we might be tempted to throw away, but near boundaries this is of importance, and we will see how this will be of importance to us later on as we look at flow near boundaries. So now in the primitive equation, the z momentum equation has the form 0 equal to minus del p del z minus rho g. So remember that the pressure and densities are all fluctuations here. We have dropped the primes. So the terms scale as p by h and g delta rho. So the ratio of g delta rho over p by h is equal to g delta rho h, and p, as you know, is scales as rho naught L omega u. This is equal to u by HL. So this, let's write it down. This is the z momentum equation. I'm just rearranging them, the terms to get to something more simplified and in terms of a certain number that we had introduced earlier. Okay, so this one, as you know, u by this is omega, u by omega L dot g delta rho h by rho naught u squared, and this is, as you know, this is the Rossby number, and just g delta rho h by rho naught u squared. Now this term g delta rho g delta rho h by rho naught u squared is called the Richardson number. This again a different number that we are introducing here, and this let's see, so this is the Richardson number, generally represented by the symbol Ri, and this is g delta rho h by rho naught u squared. So this gives us an idea of the strength of the stratification to the strength of shear in the flow. As you can see, we have the density stratification on top and we have velocity on bottom, so it gives us a ratio of approximately so it gives us a ratio of the strength of stratification to shear. Okay, so this number again is named after a scientist. So his name is Carl F. Richardson. So he's a British mathematician. He is a British mathematician, a scientist, and has a lot of contribution in fluid mechanics. You can have a look at the contributions of all the persons that I have mentioned: Rossby, Osborne, Reynolds, Ekman, and Richardson. So this is where we stopped in the discussions of non-dimensional numbers, and we'll keep coming back to these non-dimensional numbers time and again, which will give us different regimes of flows. And from the next lecture onwards, we'll discuss the boundary conditions that we had previously promised that we will discuss. We'll have a discussion on boundary conditions, and all the equations that we have derived will only have unique solutions when we define boundary conditions.